Hello everyone, and welcome to the NEATEC Electronics Series. And this episode is about high-frequency amplifier response for both the bipolar junction transistor and the field effect transistor amplifier. So let's get started. Alright everybody, so let's start talking about high frequency. So high frequency amplifier response, you have to think about, well, first off, let's back up. High frequency, when you start having high frequency going through an amplifier, things start to change. And one of the things that starts to impact the ability of your amplifier to amplify something, amplify a signal, is the internal capacitance of the device. And the devices we're working with right now are bipolar junction transistors, right here, it's a BJT, and field effect transistors, right here. And if you notice, remember this is your base coming in right here, right? Base, collector, emitter. And here you have your source, you have your gate, you have your drain, right? Now, here's the thing. You have capacitance between your base and your collector. It's called CBC, right? And you have CBE, which is your capacitance between your base and emitter. Similarly, you're going to have capacitance between your gate and your what is this? It's your drain. So it's going to be CGD. That's a D there. I'm sorry about that. If that wasn't clear, it should be a capital D. I thought it looked like a P for a second. It confused me. But anyway, that's C, gate, drain, and you also have capacitance between your gate and source. Here's your gate, there's your source, so it's CGS. All right? Now, to simplify this, there was a person named Miller. I'm going to draw his name over here. Miller. And he has a theorem. And it's called, of many things, Miller's theorem. Now, what this does is it gives you the ability to determine the input and output capacitance due to these capacitances. And this is how it's stated, all right? C in Miller, C in, it's an N, Miller, that is going to equal capacitance times AV, that's your simple gain of your amplifier, plus 1. Alright? Now, that's your gain. Alright? Now this is going to be your input capacitance. Now, we're going to do an example of this later on in this video, and we're going to make use of this, and I wanted to make sure that you knew where it came from. Now we also have something else. If we have C in Miller, we're also going to have C out Miller, okay? And let me just fix that C real quick to make sure it looks like a C. It didn't really look like a C. There we go. That's a little better. And that's going to equal something similar, but not the same. Not exactly the same, okay? So this is going to equal C out times AV plus 1 divided by AV. Let me just, you know what, I'm going to just extend these down, right? So what I'm trying to do here is just show you that if you, there you go. Now look, this right here, if AV is very large, this basically, if AV is large, this basically is going to do what? It's going to go to 1, isn't it? So at very high gain, this is just approximately equal to your capacitance out. Now remember, your capacitance out is either your CGD or your CBC, your base collector or your gate drain capacitance, depending what kind of amplifier you're analyzing, right? So you're going to need to know this because your capacitance needs to be determined when you're calculating your critical frequency. Remember, your critical frequency is going to be equal to what? 1 divided by 2 pi. What else? RC. This is what you need to calculate. You need to calculate R too, don't get me wrong, but C is something that you have to spend more time calculating for the high frequency response. That's what I'm getting at here. Alright? Alright, so what we're going to do next in the next segment is I'm going to draw an amplifier and we're going to redraw it for high frequency analysis. Alright everybody, so let's start this section by just simply drawing a bipolar junction transistor amplifier, shall we? So try this, do it along with me, because you'll get some practice, and the more you draw it, the more intuitive it becomes, really. So first let's draw this. I gotta change my color from green, but doesn't really matter, I guess. It's your AC source going ground, and the other part, this is your source resistor, right? Now, coming from your source resistor, this is your signal. You're going to come through a coupling capacitor, and then from a coupling capacitor, we're going to come to your bias resistor. So let's have your bias resistors connected here, right? So we have one here, one here. We'll call this one R1 and this one R2. All right? And up here, we're going to connect that in a minute, but that's going to be connected to VCC. So here is your gate. I shouldn't call it your gate, I mean my base, the base, because we're using the bipolar junction transistor here. It's your base. From your base, you have your collector and your emitter. Your collector comes up, you have another collector resistor, and this goes to VCC. That's what that is, VCC. Your emitter comes down, it goes to your emitter resistor, the ground, and this is RE. Alright? It's an E. Okay. And you also have a capacitor, and this goes around it as well. Now, this is a bypass capacitor. We can call this, if you want, C2. We can call this C1. And you're going to have another one tapping right off your collector, come through a capacitor, coupling capacitor, and it comes over here through your load resistor, RL. Okay, and this is up here is RC. Alright, so that is your basic amplifier there, alright? Common emitter amplifier. move it over so we have as much space as we can get. Obviously, when you're looking at this, you're gonna tap off it right here. This is your V out. It's going to supply voltage to your load, right? Now, let's start to redraw this. And let's redraw this to the a high frequency equivalent circuit. So doing that, you would simply, here's your AC source. RS, right? That's your source resistance, right? You don't need to draw your capacitor. By the way, we're going to call that one C3, but you don't have to draw your capacitor here because at high frequencies, it just looks like a short, right? So now you're going to come to your two resistors, your bias resistors. Now look, R1, I'm going to draw this in blue over here. This R1 right here. If you notice, that goes from this point directly to VCC, but remember in AC analysis, VCC is AC ground. And if you notice, R2 also goes to ground, AC ground. So they're both going to ground, right? So these two are basically in parallel with one another. Because remember, this turns to ground. So this is going to ground, that's going to ground. So we can write that, we can simplify this thing by simply coming down. And this right here, that's going to equal R1 in parallel with R2. All right? Now, if we keep on going, we're going to come right to your transistor, right? Now, let's talk about your emitter. Over here, you have this capacitor, don't you? And what do we say at high frequencies? This capacitor becomes a short, and this is bypassing your resistor. So nothing's going to see that resistance. So basically, this emitter at these high frequencies can just be thought of as going right to ground, right? Now, we have one part left. Talk about your collector, right? Remember, your collector resistor over here, this one, notice this collector resistor was also connected to VCC, which is now AC ground. And RL is connected to a ground. This is very similar to what you did with R1 and R2. So these, and your capacitor here looks like a short. So these two can be combined, and they can be thought of as a resistor in parallel. So you draw that one, and this is going to be equal to, well, I'm going to do that one in green too for you. This is going to be RC in parallel with what? RL, right? Now, there's two other capacitances that I wanted to show you that we didn't talk about here. We're going to put them in here. You have one here, and you have one here. Right? Hey guys, there we go. C, B, C, C, B, E. So, this is your collector, your base collector capacitance, and this is your device capacitance, and this is your collector base emitter capacitance, all right? And this is obviously from your base to emitter. Now, these are device capacitances. They're in the picofarads, and you would have to look at the data sheet. But at high frequencies, these things start to matter, okay? So now, if we want to include the total frequencies. That doesn't include everything. We didn't put in the Miller frequencies, did we? So let's redraw this again with the Miller frequencies. This is your source, right? RS. Got it? Now this one, we know what that is. That's R1 parallel with R2, right? Let's just make this longer to give us some room. Next, here you're going to have this right here is your C in Miller. All right? Then you're also going to have this capacitance, your base emitter. So you're going to have one here. This is your CBE. All right? Now, let's take this over here. Up, over, down. The resistances stay the same. Those are not changing. So that's going to be RC and parallel with RL. Now you have your other capacitance. This is going to be your C out Miller. And finally, we have to finish this emitter. This just comes to ground. All right. So there you have your high frequency equivalent circuit after applying Miller's theorem. Now, remember this. Why don't I just move this over to give myself some room? There is a way I can do that. All right, found some, huh? There we go. All right. Remember this one. C in Miller. That's going to equal capacitance from your base collector, AV plus 1, right? And this is your gain, right? I don't have to write that. You know what that is. And then C out Miller. That's going to be equal to CBC times AV plus 1 divided by AV. Got it? We talked about that earlier. So, I think pretty much we have it. So we just redrew this, right? And now you can see, well, it looks very interesting. There's a lot of things we can do with this. Why don't we continue with this discussion? All right, so I just moved the circuit up here, and I got rid of the previous circuits, but that's what we were left with. So at this point, let's look at this section right here. This is the input section, right? So looking at the input, if we Thevenize this, right? So we have, let's just draw it down here. It'd probably be best just to draw it, right? So if we have This is your RS. This is R1 in parallel with R2, right? Now, think about this. Remember we talked about R in base? It's this part right here. Alright? So that's the only part left. I'm talking about resistance, not capacitance right now. Just for the resistance, that's the only other resistance left, right? So let's include that here, shall we? So I'm going to call that right here to ground. I'm going to call this R in, we'll just call it base. Okay? And now over here, we're going to have two capacitors, right? We're going to have that's C in Miller, C in Miller. And then you're going to have another one, which will be your, let's draw that here. This will be CBE, your base emitter capacitance, right? So, if what we can do, since these two are in parallel, if you remember capacitors in parallel, you can simply add, right? So, why don't we just get rid of this other capacitor here? Where's your delete key? There it is. And that's going to simply be C in Miller I clicked the right one here, sorry, plus CBE. That's the value of that resistor, or that capacitor, right? So, we can also do this if we want. All right. Now, let's take this. Let's Thevenize it. So if we Thevenize it, we're going to look here, from here this way, right? We're going to Thevenize this whole thing to get the Thevenin resistance. So if you think about it, when you Thevenize something, remember for resistance, you replace your source. You replace that source with a short, just a wire, right? So when you do that, RS is also going to ground, isn't it? So all these resistors are in parallel and they're all going to ground, right? So that would actually be, if you want to think about it, if you redraw it, through a single resistor, right? And this would be your Rn, right? And then this then would go this would have a capacitor right here, and that's what we just talked about. So this would be Cn Miller plus CBE, right? And this Rn, this is going to be a long one, all right? So let's just start, I guess. RS in parallel with R1, in parallel with R2, in parallel with Rn for your base. Okay? And in this example, R in base, right? Where's my thing? Here it is. This right here in this example. This right here would be beta RE prime, okay? Now, if you go to the R parameter model of the transistor, we've discussed this before in the past, but that's how you get your R in at your base, right? So that's what it would be for this thing. So think about it. If you want to know the critical frequency, you know what R is. FC upper, right? And that's at your input, right? This is your input. That's going to equal 1 divided by 2 pi RC. Your R is right here, and this is the whole equation for R. Okay? And your capacitance is your input capacitance, and that's right here. That is your C in Miller plus CBC. All right, so that's your input. Got it? So the input is rather useful, and you're going to see that, right? Now, the other thing that has to be discussed here is, what about your output, right? So the output circuit is somewhat similar. Yeah, what can I do here? Let me see. Now for your output, you simply have these two, don't you? So what we can do there, it's the same thing. If you look at your output, right, you're coming off your transistor like this, right? This is your, I'm sorry, that's your emitters. Here's your arrow, it's coming down, you go to your ground, here's your base. But your collector, come up, you go through your collector resistor RC to AC ground. This is actually VCC, right? And then you also have your Miller out capacitance, right? You know that, and you're coming over here through, this is RL, right? This looks somewhat similar to your input lower critical frequency, but remember, what you can do here is, since these two are together, this area can be replaced by a constant current source, right? So this is very similar to a current source coming down to ground. You can then have a RC. We're just redrawing. This is all we're doing. Ground. Here's your capacitor, the ground, and here's your load resistor to ground, right? RL and C. And this is your C output Miller right here, okay? But they're all connected, so we can rearrange this, can't we? And we could make this easier. So this is really going to be a constant current source going to ground. Bring this up. Here's your Miller capacitance, right? We want to look at it like that, but actually it might be easier. I went out of order here. We can make this RL. This is going to be, like, I'm sorry, I could make that RC. This could be RL. And this would simply be your capacitance. Got it? So simply these two are in parallel with each other, aren't they? So if that's a current source, you can rewrite this as a voltage source. Come out. You can then say this is equal to a resistance, which is RC parallel with RL. All right, and through this capacitance. All right. Now, this is really what you need to get your output capacitance. So RC is simply, when you write your equation, 1 divided by 2 pi RC. Your R, this is FC upper. Your R is here. That's what that's equal to, RC in parallel with RL. And your capacitance is equal to this, which is your, what's that capacitance? This is your C out Miller. All right. All right, so I just moved the circuit up here, and I got rid of the previous circuits, but that's what we were left with. So at this point, let's look at this section right here. This is the input section, right? So looking at the input, if we Thevenize this, right? So we have, let's just draw it down here. It'd probably be best just to draw it, right? So if we have this is your RS. This is R1 in parallel with R2, right? Now, think about this. Remember we talked about R in base? It's this part right here. All right? So that's the only part left. I'm talking about resistance, not capacitance right now, just for the resistance. That's the only other resistance left, right? So let's include that here, shall we? So I'm going to call that right here to ground. I'm going to call this R in, let's call it base. Okay? And now over here, we're going to have two capacitors, right? We're going to have your, that's C in Miller, C in Miller. And then you're going to have another one, which will be your, let's draw that here. This would be CBE, your base emitter capacitance, right? So if what we can do, since these two are in parallel, if you remember capacitors in parallel, you can simply add, right? So why don't we just get rid of this other capacitor here? Where's your delete key? There it is. And that's going to simply be CN Miller I clicked the right one here, sorry, plus CBE. That's the value of that resistor, or that capacitor, right? So we can also do this if we want. All right. Now let's take this. Let's Thevenize it. So if we Thevenize it, we're going to look here from here this way, right? We're going to Thevenize this whole thing to get the Thevenin resistance. So if you think about it, when you Thevenize something, remember for resistance, you replace your source. You replace that source with a short, just a wire, right? So when you do that, RS is also going to ground, isn't it? So all these resistors are in parallel and they're all going to ground, right? So that would actually be, if you want to think about it, if you redraw it, through a single resistor, right? And this would be your Rn, right? And then this then would go this would have a capacitor right here, and that's what we just talked about. So this would be CN Miller plus CBE, right? And this Rn, this is going to be a long one, all right? So let's just start, I guess. RS in parallel with R1, in parallel with R2, in parallel with Rn for your base. Okay? And in this example, Rn base, right? Where's my thing? Here it is. This right here in this example. This right here would be beta Re prime. Okay? Now if you go to the R parameter model of the transistor, we've discussed this before in the past, but that's how you get your Rn at your base, right? So that's what it would be for this thing. So think about it. If you want to know the critical frequency, you know what R is. FC upper, right? And that's at your input, right? This is your input. That's going to equal 1 divided by 2 pi RC. Your R is right here, and this is the whole equation for R. Okay? And your capacitance is your input capacitance, and that's right here. That is your CN Miller plus CBC. All right, so that's your input. Got it? All right, so now let's talk about the critical frequency, right, which will be FC. We're talking about the upper critical frequency, U, right? And this is going to be, instead of your input, this is going to be your output, okay? Now, remember, the main equation for these critical frequencies, it's all the same, right? 1 over 2 pi RC. So the trick is calculating R and calculating C, right? So let's get rid of that here. Let's redraw the circuit. Now, if we're going into the output, come into the input like we had it, right? We already did that, so I'm not going to spend a lot of time on that. Now here's the collector. This is your emitter, right? Now, let's move it down just a tad, all right? I was drawing too far up. Now, at this point, we can draw up. We're going to go through a resistor up here to VCC, right? And this is RC. Then you're going to come out here, right? You're tapping right off the collector. You're going to come down. Remember, you have, let me draw it in here for you. So your actual circuit is going to have a capacitor in there, right? But remember, we're talking high frequency. So when you're talking high frequency, that capacitor acts like a short, doesn't it? It's just like what we did on the input. So let's just draw that straight through, right? And then we come down here. And this is RL, that's your load, right? Now we forgot something. If you recall, we have a capacitance right here. And that's that right there is called your C out, capacitance on your output, Miller. All right? Now, I called this VCC because that's what it's there, but since we're looking at AC, right, this is really AC ground. All right? And these, by the way, are ground as well. Is an AC ground right here. So if you look at it, we can redraw this, can't we? And by the way, we've already done the input and the emitter, so we're just concentrating on the output here. So the output, if you look at it, right, we can draw this. Let's draw this is your input, here's your transistor, right? Comes up. That's your collector. This is your emitter, right? Now you're going to tap off this collector, right? Because instead of running this up, we're just going to simply take this and come right down here to ground. Get it? And this is RC. Remember, RC over here, it just started. It was from your collector, and then it was connected to AC ground. This is the same thing. It's starting your collector, and it's going to AC ground, or simply ground, right? Okay, so we just moved this. We didn't change anything. We just moved it, okay? So Now, what else did we have here? We came across this. Let's neaten that up just a little bit, right? We really don't need that part right there now. Okay. Now, the next part, come over here, come down. Here's your capacitance, your Miller output capacitance, right? And then we'll come over here, and what do we have here? It's going to be your load resistor, right? So we just redrew the circuit, didn't we? Now, let's do something right here. This transistor is really can be thought of as a current source, can't it? So this one can simply draw this it's just a current source, right? So I draw that with an arrow, and the current there is equal to beta times what? IB, right? Because it's the collector current we're talking about, right? Now, what we can do here is, since these are all tied together, let's just rearrange them, shall we? So what we're going to do is just take this capacitor, we'll move it over here. We're going to then take this load resistor, we're just going to put it right here. Okay. Now we'll take this one. We'll just put this on the back here, right? So all we did is just rearrange them because they're connected there. We don't have to worry about. We aren't changing the circuit at all. We're just putting them in a different order here. That's the same circuit, isn't it? Now, let's look at this area right here, shall we? So, let's change that, shall we? We know RC and RL are in parallel with each other, right? So let's just draw this again. That's beta times IB, right? We have a resistor here. This resistor here is equal to RC in parallel with RL, right? That's what we have here. And then what are we going to have over here? Your Miller output capacitance, right? Got it? Now, think back to Norton and Thevenin. You can also draw an equivalent circuit. Here you have a current source and a resistance in parallel with it, right? Let's draw that down here. And when you do that, you can change that current source to a voltage source with a resistance in series with it, right? Now this will be known as V Thevenin. I'll put it over here, V Thevenin. And this resistance here is going to be RC in parallel with RL, right? It's just this resistance, so we just moved it right over here, right? And then what you're going to have is your capacitance right here. So, what is your equation for the output critical frequency? It's 1, let's just draw it, FCU output equals 1 divided by 2 pi RC. What is your R value? Your R value is right here, okay? Your capacitance now is your capacitor right there. And remember, that is your Miller output capacitance. And that is equal to your base collector capacitance, right, times your gain AV divided by, it's AV plus 1 divided by AV, right? So it's gain dependent. At high gains, it's pretty much equal to 1. But there you go. That is your equation for your output critical frequency, all right? Now, remember, these capacitors are connected to ground, right? So what you're going to see on the output here, let me just do this real quick. I want to remind everyone of this. Where is it? There it is. So if you're looking at a Bode plot, say you're looking at a Bode plot, right? Bode plot. I pronounced it wrong. I'm sorry. It's Bode plot, not Bode plot. So if this is your mid-range, right? That's your frequency. Well, when you hit your upper critical frequency, what's going to happen? You're going to start to turn here, right? Remember, this critical frequency is 3 decibels below your mid-range. And assuming this is either your input or output frequency and not both, it's the slope of this is 20 dB per decade. Now, suppose that's at one of your upper level critical frequencies, right? It could be the input or it could be the output, whatever you want it to, whatever it calculates to be. Now, suppose this is another critical frequency right here. Then what? Your slope changes. This slope right here now is at 40 dB per decade. That's your critical frequency right here. Right there. And that's your other critical frequency right there, right? So you can see this slope right here is at 20. This slope right here is at 40. I tried to draw it like it's 40. All right? So if it happened that these two critical frequencies laid right on top of each other, they were the same critical frequency or very close. So instead of looking like this, you would basically look like this, right? You would have two critical, suppose both of them laid right here. Well, if one of them came down and this was 20 and then this was 40, it would be this one, because you would have two critical frequencies on top of each other. So the slope of this would be 40 dB per decade. Now remember, what this means is this is attenuation, right? You're attenuating the signal, right, from your mid-range. And remember, your low frequency, you also have attenuation taking place, right? So what you end up with, just think about this, this is a key point. You have basically No attenuation between these blue lines. This is a band. You can think of this as a band pass filter. If you have a frequency in here, you're fine. A frequency on either side here, if it's over here or if it's over here, if your frequency is over here, it's going to be attenuated. Think of a radio. When you want to listen to a radio station, you turn your radio to that station. You don't want any other frequencies coming in except that frequency, right? That's kind of the concept what I'm showing you here. This, depending on your resistors and capacitances you choose, you can amplify a specific frequency and you can attenuate all the others. This is very powerful and it's used a lot. The next video we're going to talk about the same thing, except we're going to use the FET, the field effect transistors.